this is the question here. As you can see in this question, what you have is a jacket. It's basically a jacket, okay, that you wear during winter, okay, and it has 5 layers of 0.1 mm thick fabric, synthetic fabric of so and so K value, and it has 1.5 meter thick air space in between, and the air thermal conductivity is given to you here, assuming the inner surface temperature is 28 degrees, the surface area to be 1.1 meter square. Determine the rate of heat loss through the jacket when the temperature of the outdoors is minus 5 degrees centigrade and the heat transfer coefficient on the outside surface is 25 watt per meter square Kelvin. So that's the question given to you. Uh, Let me take the resistance shape. Yeah. See how many resistances I am supposed to put here. See, there are 5 layers of 5 layers. So I will have 5 resistances at least. Yeah, there seems to be a problem. Okay. Yeah. See, there will be at least 5 layers of this one. And between these 5 layers, there is airspace. Okay. So 5 layers will have at least 4 airspaces. So this is 5 and this is 4. So 5 plus 4, at least I have 9 resistances I will have. Okay. Along with this, I will have one more resistance due to convection. This is resistance due to convection. So in total, I'll have 10 resistances in my circuit here. Okay. So if I draw a resistance circuit here, yeah, it seems to be some problem here. I'll take this one directly from my practice slide. Yeah. So this is how my resistance circuit will be like. Here, what I have shown is I have shown 10 resistance circuits here. Okay. Here, this R12, R12, R5 are the resistances of thin layer fabric. Okay. And then R6 to R9 are the resistances due to the air space. And then R convection is a convection resistance. Okay. So these are all the resistances you have here. So if I have to calculate this, R1 is equal to R2 is equal to R3 is equal to R4 is equal to R5, which is equal to L by Ka, which is equal to L is
Sir, I
given.
have a doubt, sir.
Yes, please ask.
Sir, here also there is a repeating unit, repeating unit, no, sir. Why can't we take the same thing we took as above in the above problem?
Yeah. See, in the previous problem, let me go to the previous problem itself. See, in the previous problem, the repeating unit is one above the other. Okay. On this, there is a repeating unit, and there is no temperature that is present here. It is given as a one-dimensional thing. But here in this case, what he has given you is, he has given you a temperature here. He is saying that it is 28 degrees centigrade. So on one side you have the temperature, let me call this T1, which is 28 degrees centigrade. And on this side you will have minus, yeah, it is 5 degrees centigrade. So let me call this T infinity on the second side, that is minus 5 degrees centigrade. See, in between these two temperatures, you have all these resistances. Okay, in the direction of this temperature change, all these resistances are coming into the play. And these are not in parallel series, like one, not like one above the other. Okay, see here, here you have a temperature, and here you have one more temperature. That is the case here. So in between all the things you have taken. Okay, here you have one temperature, here you have one temperature. In between whatever is there, you have taken. Same way we are doing it here. Okay, see here also you can take, like these are like a repeating units also. Okay, you need not be did not say that this is not a repeating unit. Of course, it is a repeating unit, but it is simple thing. That's why I have shown it to you so that you can understand. I hope I have answered your question. Is it?
Yes, sir.
Yeah, thank you. R6, R7, R8, R9. So this is also L by Ka. This one is given the L value for the jacket is given as 0.1 mm. So it is 0.1 into 10 to the power of minus 3 converted into meters. The K value of the synthetic fabric is given as 0.13, 0.13, and the area is given as 1.1. And for this one, the thickness is given as 1.5. So let me substitute that 1.5 in meters. To convert into meters, I have multiplied it with 10 to the power of minus 3. And the K value of area is 0.026. The area is 1.1. Okay. So somebody calculate these values and tell me what are the values here. Also, we need R convection, which is 1 by HA. It is given as 25 in the question. A is 1.1. And please calculate all this values and tell me what he's asking you to find is actually Q. Determine the rate of heat loss. So he's asking you what is Q. So to take that Q is equal to 25 minus 5 by 28 is given in this. 28 minus 5 by the resistance 1 by R1. It's not 1 by R1, it is R1. R1 5 times plus R6 is 4 times plus resistance due to convection. So somebody tell me these values. Did you calculate?
Sir, R1 is 6.9 into 10 power minus 4.
6.9 into 10 to the power of minus
Minus
4
and
Kelvin
R6
per
is
watt. Please
R6
tell me.
is 0.052.
0.052. This one
0.036.
0.36. Thank you. So substitute these values into this. 28 plus 5 is 33 by 5 into R1 value is 6.9 into 10 to the power of minus 4 plus 4 into 0.052 plus 0.036. Tell me this value. Okay.
So 370, sir.
Huh?
370.
Q value is 370. Yeah?
No, 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 sir. No. Somewhere away. I'll check again, sir. Wait.
133.36.
133.36 watts is your Q value. Good. Okay. Now, whatever Q you have found is the Q value for 5 layers. Okay. Now, let me find the Q for one layer. Okay. With this, you are done with your question. Okay. But I would like to give some insight into it. For that reason, I'm going into a concept here. For that, I'm taking T1 minus T infinity till by L by Ka plus 1 by HA. So what I have taken here is just I have considered that there is only one layer of this kind of material instead of 5 layers. So if this is the case, somebody help me calculate what is the value. So this L by Ka is 6.9 into 10 to the power of minus 4 plus 0.036. Tell me this value, Q of one layer.
899.4.
899.4 watts. See, you look at these values. Okay, if Q is one layer, it is 899.42. See, if the temperature outside is minus 5 degrees centigrade and the person is wearing only one layer, it is going to lose almost 1000 watts of heat to the atmosphere. If you are losing 1000 watts of heat to the atmosphere, it will be huge heat loss from your body. If that is the case, you are going to shiver like anything and you will be feeling a lot of discomfort because of this reason. But if you have so many layers of insulation, the heat transfer has reduced almost by 1/10 part. Okay, when it is reduced by 1/10 part, when your body is rejecting just this 100 watts of heat, you'll feel much better. Okay, the thermal comfort is excellent. Okay, so the thermal comfort in this case will be very good. You got the point? I hope you got the practical viewpoint behind this particular problem. Okay, the reduction in heat transfer you must have observed, and its influence on your comfort, on the human body comfort, is actually understood very well using this particular calculation. And this is one way of looking at it. Okay, Uh, you have used the fabric itself. And the second case, let me have a wool. Okay, and the thermal conductivity of the wool is taken as 0.035 watt per meter Kelvin. This is the value, you take it, and using this value, you try to calculate what is the thickness of this particular wool that has to be obtained when you want this particular thermal comfort. That is, if Q is 133.33 and your outside atmosphere, your body temperature is 28 and the outside atmosphere is -5, and you want the thickness of the wool, okay, whose thermal conductivity is 0.035 and the area is 1.1 plus 1 by 25 into, this is 1 by HA I am taking, into 1.1. If this is the case, tell me what is the value of L. See, what I have done is I have taken that Q is equal to T dot T1 minus T infinity 2 by L by Ka, and this is for wool I have taken, plus 1 by HA I have taken. So somebody tell me what is the value of L. What is the L value?
8.12 into 10 power minus 3.
8.12 into 10 to the power of -3 meters. So that will be equal to 8.12 mm. See, 8 mm is almost like your 1 centimeter. Okay. See, imagine you have 1 centimeter thick wool on your body. Okay. Will you be comfortable with that? Okay. Or will you will have L of synthetic fabric, and this L is 0.1. This is 0.1 into 5 plus 1.5 into 4. Okay, tell me this value. 0.5 plus, this is like 6, right? This is 6.5 mm. Okay, if you have to use this synthetic fabric, you'll be using 6.5 mm. And if you have to use wool, it is 8.12 mm. And you imagine which one will be more comfortable. Okay, this one will be more comfortable because it is providing same thermal comfort with lesser thickness, and even weight of it will be very weight of synthetic fabric will be less than weight of wool. So people will obviously prefer this one compared to the wool. Okay, that's why most of the times we are going with this synthetic fabric one. Uh, So that's all from my side in this particular problem. If you have any questions in this problem, you can ask. Yes. Do you have any questions? No questions? Right. Don't have any questions. Let me move forward. See, till now in this composite wall problem, what we have done is in composite wall problem, we have taken so many practical problems. The practical problems are like your single pane window and then double pane window. I have taken double pane window. And what else we have taken? We have taken the example of the concrete wall. When it's a concrete wall, it's a brick wall. Brick plaster wall I have taken. This problem we have solved. And what else we have solved? We have solved the this problem, jacket problem. We have solved. And this wood siding problem we have solved. And then this problem. These are not like practical problems, but they are also like the resistance constant problems are. So what I missed here is your wood siding. So all these problems are the practical problems that you can use to apply your composite wall concept. Okay, all these problems will have the resistance. It is all resistance in parallel or combination of the both, and then you apply this particular concept, and you'll be in position to design what is the Q value, and then with the help of this Q value, you can define whether you want more heat transfer, whether you want less heat transfer based on the situation. Likewise, many problems can be used here, like one more problem I will tell just now, furnace wall. Okay, furnace wall, if you take, it will be made of so many layers. Okay, you will have as high as 1800 degrees centigrade temperature inside, and the atmosphere temperature is around 25 degrees centigrade, and you don't want the heat to transfer to the outside. For that purpose, you should have so many refractory bricks. Okay, refractory bricks of very less thermal conductivity should be taken, and when you take this less thermal conductivity refractory bricks, and the heat transfer will be reduced. What thermal conductivity refractory brick will you take, and what will be the thickness of each one? How do you decide? And all that is dependent on this particular concept. Okay, this kind of problems you may get, and any kind of problem from any practical case you may get. So I request all of you to go through all of them. I hope I have given you a clear idea of how this particular composite wall problem can be applied in various practical cases. Okay, with this, I close